Hello.
Hello, we cannot hear you.
Слышно, ребят?
Да, теперь слышно.
Но это я говорю просто, это не преподаватель.
А.
Меня слышно?
Да.
Да.
Так.
Раз два почему-то.
О, Коротоножкина слышно. Все. Очень приятно.
Добрый день.
День добрый. Все в порядке, видишь?
Да, вижу.
Здрасте.
Это проблемы не у нас.
Что Филипп исправился, а то я бы обиделся очень сильно.
А?
Чуть не обиделся на фамилию.
А?
Б, давай.
Ну, очень сложно вообще. Русский язык очень сложный, я считаю. Давайте разговаривать по-английски.
Кому-то слышно? Или никому не слышно опять? Вот.
Слышно?
Да, вот, да, теперь слышно.
Okay. Let us try to speak English.
И видно.
Very good. So I have sent you a link to a board. Can you see it? This one. Yes. Ребят, опять не слышно, что ли? В чем дело?
Слышно.
Слышно,
Слышно,
да.
всё
Но
слышно.
нам требуется доступ к разрешение на доступ к доске.
Разрешение доступа к доске. Вот. Okay. At least I can write. Mhm.
Yeah, right now we can join it, so it's okay.
Okay, and you can write.
I guess no, we just can see it.
Sorry. Oh, yes. Now you can write. Yes. Okay, thank you very much. You can write. Let's begin. Please write on the if you have something to say. Don't play with it. Okay, now let's begin with our lesson, and you have a list with problems from Wiki, yes? Everybody have a list with problems.
Yes.
Okay, let us begin with the first problem. How many operations, binary operations on the set with n elements? Do you have some ideas? You can write to the chat or you can say. Okay, I see one variant and is there any other variants? Okay, just you can try to guess or think about it. There are some variants except n in power n. Okay, there is another variant from the same student that it is n power n squared. Okay, this is incorrect and this is correct. Can you explain why this one is good?
I'm sorry, could you please check your microphone connection because it's like really, I don't know, the sound is really bad. It's like really bassy, you know? Кряхтит он, в общем.
I'm sorry, but I don't know why. Okay, I don't know if it's better, it's good, but I haven't changed anything. So the question is, please don't write on board anything else except our problems. So this is correct answer. Can somebody explain why it is correct? Is how many operations it is problem one. How many operations on the with n elements. So the answer is n in power n square. I ask somebody to explain why. It's better if you explain orally, not in the chat, but we can hear you.
So could anybody hear me?
Yes.
Okay, we know from combinatorics that if we have sets A and B, and A has m elements, B has n elements, their n to power m maps from A to B. And for this particular case of binary operation, we have sets s squared to s. So s squared has n squared elements, and s have just n elements. Thus, we have n to n squared.
Yes, it's good. So let me write this explanation. If you have two sets, A and B, and the order of A is M and the order of B is N, so, and you are interested in maps from A to B, then you have how many maps? M in the power n or n in the power m? How many?
It should be m to
n
power n.
m.
Yes, n to power m. Here, this is s multiplied by s. So there are n squared elements, and this is s. So there is n elements, and so n in n squared. I have a little bit frames, so I'm sorry. There is my contacts. If you have some questions, you can contact me with this. And this is write down the same explanation for the first problem. Okay, the second problem is write down this for n equal to, but we want to write it explicitly. There are 16 variants, and is there some ideas how to get there?
Can I ask a quick question? Will you post this presentation online?
I don't want it because there are some proofs for problems for the following problems. So I want you to solve yourself. At the end of seminar, I can send you.
Yeah, I've meant that after the summer, just so we have the solutions for the problems.
But there are just a few of them.
All right then.
Теперь звука вообще нет.
Вы просто, похоже, случайно нажали на выключить звук. А, вот теперь должен быть. Нет, опять снова нет.
Can you hear me?
Yes, yes.
There are some problems with my microphone. I shall try to change it, but now I want you to think about try to write down some variants, not all the 16, but some of them. Okay. On the
I have changed. Oh, sorry.
I have changed my microphone. Now, can you hear me?
Yes.
Yes, much better.
Okay. Good. I'm sorry for these problems. I guess it only for the first time. So we try to solve the second problem. Can you write down some variants for these binary operations on the set in two elements? If there are some ideas. Okay, you have two equalities. Let me show it for all of them, of you. A multiplied by B equals A, and B multiplied by A equals B. Oh, sorry, in your it's equals to A. Is it enough to know just two equalities to know all about our operation, or we need something more?
Maybe we should establish the neutral elements and the inverses one.
No, not always there is a neutral element. So we discuss all the operations, but if there are just two variants here, A and B, yes, and there are two variants, A and B. So we have only 4 operations, but we know that we have 16 operations. So that is to know A multiplied by B and B multiplied by A is not enough to know all the operation. What shall I write down except A multiplied by B and B multiplied by A? What can be multiplied? We have two elements, A and B. And we want to multiply all the elements. So we can multiply A with A. We can multiply A with B. We can multiply B with A. And we can multiply B with B. And for every couple, we have two variants, A or B. So for each row, we have two variants, these two, these two, these two, and these two. We multiply all of them, and we have 16 variants. Do you see that what I write? Yes.
Yes.
Okay, and if we want to write down all of the operations, we can write a table. Here it is. So this is a table. We have left part, A, the first row, corresponds to multiplying A by A. The second row is A multiplied by B. The third row, B multiplied by A, and the last row, B multiplied by B. And columns corresponds to variance. There are 16 columns on the right part, and each of them gives an operation. For example, column number 5 give this operation. Okay, it's clear?
Yes.
Good. And I want you to think about okay, there is a question. We need to explain how the operation deal. So we need A multiplied by A. We need explain what is A multiplied by B, B multiplied by A, and B multiplied by B. So we need 4 multiplying four products, and for each product there are 2 variants. Let us put it in the table. The first row of the table is the result of multiplying A by A. So first 2 columns is just what we are multiplying, and the other columns is the result. So if we have, for example, 5th column, then 5th column A, B, A, A. So A multiplied by A equals A, the first element of this column. A multiplied by B is B, the second element of this column. B multiplied by A is A, the third element of column, and B multiplied by B is B. This is the 1, 2, 3, 4. It seems that there is a mistake because the last element of this column is A. Let me try to I'll try to okay, I'm sorry. Now it is correct. It is not a multiplication, it is not composition, but it is some operation. But most of all, we shall call any operation by multiplication. So it's very long to say operation of A and B. So we just say A multiplied by B. Okay. Now let us try to explain if this operation is associative. Just this number 5. Is it associative? Maybe somebody shall write. For example, I don't know you, unfortunately, but I see some of you. For example, Alex Lakeev. Can you write something about?
Can I ask a question about like the last task?
Okay, the last task is we have operations, just operation number 5, this one. And we need to check if it is associative.
What kind of number 5 in the PDF file?
On the bottom of my table.
I just don't see the numbers or anything.
Okay, I shall write it on the board, and you check if it's associative. So A multiplied by A equals to A multiplied by B equals to B, B multiplied by A equals to A, and B multiplied by B equals to B. So this is the operation, and please check if it is associative. Do you understand what kind of checking should you do?
Not really. Like for the property. Okay. Like, but I see there are only like 2 elements, and for associative.
The associative operation is X multiplied by Y multiplied by Z equals to X multiplied by Y.
Yes.
Yes.
I
Now,
just don't get where do I get that if I have like only
X,
and Y.
Y, and Z. You can just substitute, for example, I don't know, B,
Okay.
or something else. If you have that there is no equality, then you checked that this law is not associative. If there always is equality, then it is associative.
So I either check all of them, like AAB or ABA, like all possibilities, yes, or get an inequality.
Yes.
Okay.
And do we check it for like a given operation that has like a definition of its multiplication, or for any of them?
Sorry.
Like, do we check associativity when we know that, for example, A by A is A by B is B, and it's like A, B, B, A, for example, and we can check for like this case, or do we check for the common case?
We check if we want to explain that there is no associativity, then we must give an example when associativity is not the case. And if we want to check that we have associativity, then we must either either all variants check, all prove something in common case.
Yeah, and we prove it. If we prove it, then we know that any binary operation for such a set is associative.
Not just this binary operation.
Oh, this. Okay. Mm-hmm.
Okay.
So like for this case it works, but we need to also to check like ABA and all others.
Okay. We want to find the variant when there was not equality. This operation is not associative.
Okay.
I'm sorry. Sorry. Here is A. I'm sorry. B multiplied by B equals to, equals to A. Yes. Here is B multiplied by B equals A.
Well, then something like BBB will be contradiction.
BBB
Yeah.
is B, let me try it. B multiplied by B, B is, it is A.
Yeah.
A multiplied by B equals B, but B multiplied by B multiplied by B, this is equals to A, and B multiplied, yes, it is A. Okay, this is the contradiction, and this is not associative.
Yeah. Okay.
Okay, thank you very much. And I'm sorry, if we want to check the first operation, A multiplied by B equals A multiplied by, sorry, A multiplied by B equals B, B multiplied by A equals A, and B multiplied by B equals B. I have done a mistake, and our operation was this one. So this is associative operation. I don't want to check all the variants. How can I explain that this is associative operation? Is there any explanation that this is associative? It is a very simple explanation. Okay, we have not very much time because I had some problems with my microphone. So let me explain. I think that if we have this operation, then, oh, sorry, let me just x multiplied by y. This multiplication equals y. So this is a very simple operation. It is not, it doesn't depend on the first multiple. It's just depends only on the second one. So if we have this one, it is equal to z, and this one also equal to z. Okay. I haven't catch the last explanation. Is it clear? Okay, thank you very much. Now let us proceed, and we want to have some operations with permutations. So we have a concept of a group. Let me remind you that a set G with a binary operation which we call multiplication is a group. If three axioms occurs, the first is associativity. The second is there is a natural element which we call E, such that E multiplied by X equals X multiplied by E equals X for every X. And the third one is that for every G in G, there is G in the power -1, such that G multiplied by G minus 1 equals G minus 1 multiplied by G equals E. So now the question is that S3, the set of all permutation of order 3 is a group. Can you guess what is the neutral element?
What should we say again?
If we want to say that this set is a group, we need first of all an operation. What is the operation among permutations? How can we multiply two permutations? Yes, this operation is composition. So we have composition and we want to check the first axiom, associativity. So associativity we will check later, and we proceed with the second axiom, which is existence of neutral element. So you're right that neutral element is identity permutation. So this is a permutation which is, if you have a composition with any other permutation, then we have this other permutation. And how to get the inverse element. So if I have, for example, G, this one, what is the inverse element, inverse permutation? Switch top and bottom. Yes, of course, I would like not switch, but permute something. So this is a permutation which gives such permutation. 1 goes to 3, 3 goes to 2, and 2 goes to 1. This is a cycle. So to have the inverse, we want to wrote this cycle in opposite way. So here 2, here 2 goes to 3, and here 1. But switch open and top and bottom is correct. And I would like to check that you can compose these permutations. So please, can you write down what is it? Can somebody write down what is the result of this multiplication? I'm sorry, but there are one on the bottom. This equals to 2. It's my mistake. I'm sorry. So let it be 3. Three here, but it's not very good. Yes, the last variant is correct.
Thanks.
This one is correct, so it should be here. Unfortunately, it is erased. So okay, let me explain how to multiply permutations. We have 1 on the right one. It goes to 3. We find 3 on the left one, and it goes to 3. So 1 goes to 3. We have 2 on the right one. It goes to 1. So we find 1 on the left one, and it goes to 2. So 2 goes to 2. And 3 goes to 2, and 2 goes to 1. So there is 1 here. Yes, it's correct. Okay. So how can we check that composition is associative? The main problem, we have checked that the axioms 2 and 3 is good, so they occurs, but the first is associativity. We haven't checked. It's a kind of writing, so let me write something. Phi multiplied by psi multiplied by tau from x. It equals to phi multiplied by psi from tau from x. And it equals to this one. If you write down this one, you will have the same. So this proves that composition is associative. Okay? Is it clear? It's rather simple, but you need some deal with this composition just by definition.
So we do not prove the associativity just because it goes out of the definition of permutation, or what?
By definition of composition, I think.
Oh, okay.
Okay. Now let us think about even permutation. So we have a group AN. It consists of even permutation. I think that it is a subgroup of all permutation. How can we try to check it? What is the definition of subgroup? Can somebody say me the definition of subgroup? If we have a group G and a subset H, what shall we check to say that H is a subgroup?
Each element of A must contain the inverse element.
If we have H in H big, then the inverse element should be in H big. But this is not the first. Yes, the first is that if we have two elements, H1 and H2 from H, we should check that the multiplication belongs to H big. This is the first. This is the third. And the second is that the neutral element belongs to H. But the second is very simple, and it follows from the first and the third, because if we have some H, then which belongs to H big, then H minus 1 belongs to H big, and then the multiplication H multiplied by H minus 1 equals to E, and it belongs to H big. So the second follows from the first and the third, but the only one exception that if H big is empty, then the third does not follow from first and third. So this is equivalent to H big not equals to empty set. So this is a very simple condition, and the first and the third is the condition which we need to check. So how can we check it in our situation where we have AN in Sn? This one. The first one, we need to check that if we have two even permutations, that their multiplication is also even. I guess that you know this rule, yes? Do you know what is the result of multiplying even permutation to odd or odd to odd? Something about this.
Even multiplied by odd is always even.
Even multiplied by odd is odd. I'm sorry.
Could you just clarify what's even and odd permutations?
Okay.
Because I don't think we had this in linear algebra.
Sorry for this.
We had permutations, but not even odd and stuff.
Okay. You have not such conception, yes, in linear algebra. If we have a permutation, for example, this one, then a pair, for example, this one, is inversion if you have this is sigma, you have 1 less than 2, but sigma of 1 bigger than sigma of 2.
I guess we've got these notations in linear algebra, but it was like not used a lot.
Okay, let me proceed. This is the concept on inversion, and then sigma is even if there are even inversions, and sigma is odd if there are odd inversions. But it is very difficult to deal with permutations in such a way. We have such a rules.
Igor,
Multiplied by even equals to even one. Even multiplied by odd equals to odd one. Odd multiplied by even equals to odd, and odd multiplied by odd equals to odd. Oh, I'm sorry, equals to even. So when we multiplied two permutation, then there I don't know how in English четность.
It's parity.
Parity.
Yeah.
So the disparity of the result is the sum of the disparity of each multiples. So even plus even equals even. And this is the reason why even permutation multiplied by even equals to even permutation. Okay? So this is the rule. And if we want to check that AN is a subgroup of SN, this is the set of all even permutations. So we need this one because we need, let me show, oh, we have no previous slides. I'm sorry. We need to check that if two elements belongs to AN, then the result of multiplication belongs to AN. So this is the rule which give this one. So the first rule is, let me write once more. If we have if we have H1 and H2 from H big, so we need to check that the multiplication belongs to H big. If H big equals to AN, then these two are even permutations. And since this is even permutation, it belongs to AN. It's okay? Is it clear? Please say something.
I'm just a little bit lost, but I guess it's clear. So if we multiply two evens and then
If we multiply two even permutation, we have even permutation. So this is just some property of multiplying permutation. I suggested that you know it from the course of linear algebra.
yeah. Now I remember that we had this, but it was just a different name. And what did we get? Like, do we prove some like axiom of a subgroup from the parity of these permutations, or what?
Yes, we want to check that AN is a subgroup of SN. What is this subgroup? By definition, this is a subset such that if we have two elements, then multiplication belongs to this subset. So this is just checked that if it is even, then the result is even. So belongs to here. And we need to check one more. If H belongs to H big, then the inverse element belongs to H big. How to check it? This is also just a property of permutation. If sigma is even, then sigma in power -1 is also even. Why? Because sigma multiplied by sigma -1 equals to identity, and identity is even. And this one is even. This follows that sigma -1 is also even. Okay? And the second, this simple rule that identity belongs to AN, this is right. Identity is an even permutation. Okay?
Yeah, okay, now it's clear.
Okay, please don't erase this board, because maybe somebody want to see on it after the seminar. So let us talk about matrices. We have some problems about matrices. For example, number 11. Why GLN is a group? With multiplication. Do you know what is GLN? What is it? Okay, this is the set of matrices with non-zero determinant. So GLN, this is all A from matrices n times n, such that determinant of A does not equal to 0. So why is this a group? Why GLN is a group? Let us check. First of all, associativity. I think you know it that matrices squared matrices is multiplication of square matrices is associative. This is right. The second, we need a natural element. What is it? Yes, you're right. Good things. So the natural element, what is it? It is just this matrix. Oh, I'm sorry. What is the denotation of this matrix? E or this one?
The second one, I guess.
The second one, yes. Okay. So this unit matrix is a natural element. Okay, and the third is if matrix has non-zero determinant, that it has inverse one, and determinant of this one also non-zero. So this element, this matrix A minus 1 belongs to GLN. And so we checked that GLN is a group.
But isn't the property of a group that G by G in the power minus 1 is the identity?
Of course, but it is right. This is just the definition of minus 1. So A multiplied by A in power minus 1 equals to natural element. But this is just the definition of inverse element, but this is right.
Yeah.
Because, A minus 1 is inverse matrix. Okay. The second question, if this set of matrix, is it a group? If this set with multiplication is a group. Oh, no, it is not true, because we have the first axiom is associativity. This is true. The second one, we need a natural element. The same element is natural. This unit matrix is a natural element. But the third axiom say that for each A, we need the inverse one. But now we correspond all the matrix. For example, there is just zero matrix. And if we multiply a zero matrix to another matrix, you always have just zero matrix. This is not equal to identity matrix. So, okay. So we have checked that all matrix, all square matrix are not a group. So, now I want to talk about this group. This is the group consists of all reminders when you divide to n with operation of sum. So do you understand, for example, in Z5, what is the result of 3 plus 4? Yes, the result is 2 because this is 7, but 7 equals to 2 because we want just reminders by modulo 5. So in Z5 you have elements 0, 1, 2, 3, 4. If you want, you can say that 3 equals to 8 equals to 13 equals to -2. But this is the canonical elements, and if you sum 3 and 4, then you have 2. I have, I'm sorry, the table of addition in Z3. It is rather simple. This table is rather useful if you want to write down all the sums or all the multiplications. And now we want to discuss one more group, which denoted by Zn with star, Zn star with multiplication. What this group is? So this consists of all elements M such that M and N, I'm sorry, M from Zn, such that this common greatest common divisor of M and N equals to 1. So these two numbers should be relatively prime. For example, the group Z5 star consists from what elements? Can you just say what elements belong?
0 to 4?
From 0 to 4?
Maybe
No,
from 1 to 4.
from 1 to 4, because 0 greatest common
Doesn't
divisor
really have a great common divisor, right?
is 0 and 5 equals to 5. It's not obvious because 0. Okay, this is two elements, 3 and 4. And for example, Z6 star, how many elements here?
So it's 1, 4, 5.
No, 1 and 5.
Oh yeah, yeah.
4 is have greatest common divisor 2. And this set is if we multiply two elements of this set, we have the element of this set. For example, in the second part, 5 multiplied by 5 equals to 25, but if we divide to 6, it is equal to 1. So it can be proved that this 1 is a group with multiplication. Okay. And the last question is about order of element. If we have G an element of G, then order of this element G equals to minimal natural n such that G in power n equals to the natural element. If there is no such n, then this order is infinity. So if we have group Z with plus, what is with addition? So what is the order of, order of 1? And what is the order of 2? Of 0, I'm sorry. The order of 1 equals to infinity, because if we have 1 plus 1 plus 1, and what is the natural element of this group? Do you know what is the natural element of this group? It is, yes, 0. And the order of 0 is just 1, because 0 we need to add with itself just 1 time, and we have 0. And I'm sorry, 2 minutes more. Let us try to solve a difficult question. Number 17. Do you have an element from GL2? It is just a matrix of order 14. Let us begin from a matrix with order 2. If do you know some matrix with order 2? Here's multiplication, and the natural element is unit matrix. So we need a matrix such that A square equals to E. Do you know some matrix? No. Why a square T from this is just this matrix. or this matrix. Then it in power 2 equals to E. And to have matrix with order 13, we can take such a matrix. Sorry. This one. This is the matrices of rotation to the angle to this angle, 2 multiplied by p divided by 13. So if we rotate 13 times this rotation, then we get to identity to the identity rotation. Is it clear? Okay, thank you very much. You have some homework which you need to send to assistant. So I send these slides and this link to your email, and thank you very much.
Thank you.
Thank you.
There is a mail address of assistant on Wiki.